All right, good day to you all my viewers. In this video, I'm going to take you through the laws of indices, and I will also show you some examples of how to apply this law in solving indicial expressions. All right, let's go. Now, the following laws are true for all values of a, b, and x, given that x is not equal to 0. Law number 1. If you have x raised to power a times x raised to power b, x and x, and since they are common bases, you can pick one s and express the whole thing as s raised to power a plus b. In other words, whenever you have common bases and then multiplying each other, or you have two or more common bases multiplying one another, what you have to do is to just pick one out of the common bases and then add up their indices. As you can see it from here, let me pick my pointer. You can see that we have x raised to power a, and we have x raised to power b. All right, multiplication sign between them. Then I pick one x and then add up their indices. So you can have x raised to power a plus b. Okay. The example where this is applicable is the solution to exercise Roman figure 1. As you can see in exercise Roman figure 1, okay, look at the exercises we have. Exercise Roman figure 1, we have 10 raised to power 5 multiplied by 10 raised to power 4. And then solution to that is saying here, you can see that 10 raised to power 5 multiplied by 10 raised to power 4 is equals to 10 raised to power 5 plus 4, because 10 and 10 are common bases, okay? And you pick one base out of the bases, the two bases, and then add up their indices. So you have 10 raised to power 5 plus 4. And that's how we arrive at 10 raised to power 9. Okay. Move to the next law, which is the second law. The second law says that if you have s raised to power a divided by s raised to power b, is the same thing as s raised to power a minus b. So this law says that if you have two or more common bases, you pick and you have division sign among them. What do? You pick one base and then subtract their indices accordingly. You can see that this is a minus b, not b minus a at the power level here, simply because a comes before b in the arrangement at the left hand side. Okay, and the application of this is seen in the solution to exercise Roman figure 2. And what's exercise Roman figure 2? That's 22n raised to power 7, as you can see here, divided by 2n raised to power 3. Okay, and by simplifying that, we have 22 multiplied by n raised to power 7 all over 2 multiplied by n raised to power 3, because we need to separate number from alphabets. Now, after we've done that, 22, 2 can go into 1, and then 2 can go in 22 11 times. So you have 11 here. Then you have n raised to power 7 divided by n raised to power 3 that is left over. What do? You pick one by applying the second law. Just pick one out of these common bases and then subtract their indices accordingly. And that's what we did, as to arrive at n raised to power 7 minus 3. So we pick 7 because 7 comes first, and then subtract 3 from it. So we have 11 multiplied by n raised to power 7 minus 3, and 7 minus 3, that's 4. So that's 11 times n raised to power 4, which is the same thing as 11n raised to power 4. Okay, now the next thing is let's look at the third law of indices, the law that has to do with negative power. Okay, whenever you have negative power, the negative sign is represented by 1 all over in the simplifications of the original expression. Okay, the negative sign is represented by 1 all over. So, and the remaining part of the expression comes under the 1 all over as denominator. Let's look at the applications of this law. Okay, and that's seen in exercise Roman figure 3. Okay, exercise Roman figure 3. We have to simplify 5a raised to power minus 3, which can still be rewritten as. So I want to take you through how we arrive at this answer, and please follow me. So this can still be rewritten as 5 times a. Okay, 5 times a times a raised to power 0, okay, minus 3. 5 times a raised to power 0 minus 3. And this will give us, of course, this will give us 5 times a, 5 multiplied by a raised to power 0, all right, multiplied by a raised to power minus 1. And of course, you know that a raised to power 0, by the applications of the third law, a raised to power 0 is 1. So you have 5 times 1, okay, multiply by a raised to power 3. Sorry, this is a raised to power minus 3. Okay, a raised to power minus 3 is the same thing as by applying the fourth law, is the same thing as 1 all over a raised to power 3. Okay, and that give you, by multiplying the whole thing, now you have 5 times 1 times 1, which is 5. Okay, which is 5. Then all over a raised to power 3. That's how we come about 5 all over a raised to power 3. This is applications of the third law and the fourth law. Okay, now let's look at the fifth law. The fifth law, that's the multiplications of powers. So if you have x raised to power a, everything put together into brackets, raised to power b, is the same thing as s raised to power ab, or s raised to power a times b. Okay, and with this, okay, let's move on. Then we look at where to apply it among the exercise. Then we have the sixth law, which says that if you have s raised to power 1 all over b, is the same thing as bth root of x raised to power 1. Of course, the one is not written, but is there. Okay, so, and take note of that, and let's take law 7, which says that if you have x raised to power a over b, is the same thing as b root of x raised to power a. If you notice very well, you see that I said 1 is a, x raised to power 1 is what we have here, but it's not written. We just put, just like ordinary number written, or ordinary value written, is a value raised to power 1, but the 1 is not written. You don't need to write it. A mathematician will always know that there is 1 there. Okay, so the same thing happen here. So you can see in the place of 1 in law 6, you have a. So you have b root of a, s raised to power a. Take note of that. In other words, if you have fraction per power, the numerator will always come as the root of the base, and the denominator will be the power of the base. That's what this law says. And the very good example of the applications of this law is seen in the solution to exercise Roman figure. That's exercise Roman figure. Let's look at exercise Roman figure 5. Okay, let's take exercise Roman figure 5. Let's take exercise Roman figure 5. Let me walk you through exercise Roman figure 5. How we apply the seventh law, from which you also see, you will also indirectly be seeing how sixth law is applicable. So let's look at that. And this is 16 all over 81, everything put together, raised to power minus 3 over 4, okay, which is the same thing as, this is the same thing as 1 all over 16, okay, by the applications of the fourth law, 1 all over 16 over 81, okay, over 81 put together into brackets. All right, raised to power, the power now without negative sign, since 1 all over is representing the negative sign, okay, raised to power 3 over 4, and this is equals to, this is the same thing as, this is the same thing as is the same thing as saying take the inverse of 16 all over 81, and of course that's 81 all over 16, okay, then put the power, put them in brackets, put the power. All right, so that's 3 over 4 at the power level, okay. Now this expression, by the applications of the seventh law, can be written as fourth root of 81, okay, fourth root of 81 all over 16, okay, which is okay, everything put into brackets, raised to power 3, the numerator you have at the power level here, raised to power 3, and then that's equals to, if you look at this, fourth root of 81, that will give you 3, okay, because 3 raised to power 4 will give you 81, and then fourth root of 16, that will give you 2, then the power there in its position, so the whole thing raised to power 3, and this is the same thing as 27 all over 8. This is equals to 27 all over 8, because 3 raised to power 3 will give you 27, okay, that will give you 27, and 2 raised to power 3, that will give you 8. So you have 27 all over 8, and that's how this is how we arrive at 27 all over 8 that you see here, okay. 27, this is how we arrive at 27 all over 8 that we see here. So this will end this video, and I will urge you to be on the watch out for the next video that we bring. I will upload. Kindly subscribe, upload. Kindly subscribe if you have not subscribed to this channel, and also share this video with all the students that are around you. Thank you.